Hi everyone. So today we're going to talk about curvature, which is a notion that a lot of you have a nice intuitive understanding of also, and we've even used the term in class before, but we've never talked about rigorously. We've never given an actual definition of what the curvature of a surface really means, what we really mean when we're saying that. And a lot of the work that we've put in the last 2 weeks is going to kind of come into play and allow us to do this in a really nice way. So let me start by giving a summary. Summary of the tools that we've obtained so far that we're going to use. So first, you calculated the area of a triangle on a sphere. Let's say of radius rho. And the area of that triangle, it turned out, only depends on the interior angles of the triangle. And the formula was given by rho squared, the radius squared, times alpha plus beta plus gamma minus pi, where these are the interior angles of the triangle. And in the last couple lectures, I showed you how to get also the area of a triangle on the hyperbolic plane. Again, let's say hyperbolic plane of radius rho. And so if you've done this exercise, then you were able to calculate that the area of this triangle was rho squared times pi minus alpha plus beta plus gamma. So it really looks very similar to the formula for the sphere. Sorry, these should be in parentheses here. It's the negative of the formula for the sphere, but notice that if we're on hyperbolic space, the sum of the interior angles of a triangle is less than pi, and therefore this formula is positive on hyperbolic space. So that's a good sanity check. So if you did the exercise from Wednesday, you were also able to calculate this area. And then finally, the other tool that we're going to need is the holonomy of a triangle. And this formula works on any surface. It could be the plane, could be the sphere, could be the hyperbolic plane. And I'm going to denote the holonomy by script h of delta. And it was just given by alpha plus beta plus gamma minus pi. Now notice that when we're in the plane, alpha plus beta plus gamma equals pi, and the holonomy is just 0. Okay. So we're going to use those tools. The first question I would like to ask you is the following. Is there an intrinsic way to calculate the radius of a sphere? So this is sort of a motivation for talking about curvature. And intuitively, you might say yes, because if you're on a curvier sphere, you know it has a smaller radius. Let me say what I mean. By intrinsic, I mean that you're not holding the sphere, so you can't actually measure the radius. Again, intrinsic means that you live on this sphere, so maybe you're a bug. Can this bug measure the radius of the sphere? Now, of course, if the bug can walk in a straight line, then the bug could just travel along a geodesic until it comes back to where it started, measure the circumference, use that to calculate the radius. But I'm going to place more restrictions on you. Let's say that the sphere is very large compared to the bug. And a good example to be thinking of would be like us living on the Earth. Is there a way for us to calculate the radius of the Earth without, going into space and actually measuring it from an extrinsic perspective, and without traveling all the way across the Earth? Well, actually, I did some internet searching, and so the answer is yes, as you might expect. The first person, at least that the internet knew of, to actually do such a calculation was an ancient Greek astronomer named Eratosthenes, which was an astronomer from the 2nd century BC. So that's the earliest calculation I could find where someone was able to measure the radius of the Earth. And the way that they did it was kind of cool. Looked at 2 different cities and chose some tall buildings and used the sun to measure the shadows of these buildings and use those shadows to calculate the radius. And so the idea is that the sun's really far away from the Earth relative to the size of the Earth, and so we can assume that all the sun's rays are coming into the Earth from the same direction. And to make our lives simple, let's assume that we do the measurement from a city and at exactly the right time so that the sun projects no shadow from this building. Okay, and actually that's exactly what this astronomer did. And let's say that the distance between these 2 cities. And then you can measure the shadow, the length of the shadow here. Okay, and you want to do this measurement at the exact same time, of course, so that the shadow doesn't change as you go from one to the other. And what you'll notice here is that this angle is going to be congruent to that angle, and so you've got similar triangles here. And so I claim that you should be able to use this picture to calculate this radius r. One kind of interesting little fact that I found when I was reading was that, of course, this was in the 2nd century. They didn't have cell phones, so they couldn't just measure. He couldn't do 2 simultaneous measurements in 2 different cities. So what he did was he did the measurement in city 1 at a certain day, and then did the measurement on the exact same time and day a year later in city 2 so that the shadows would match up. Okay, so maybe pause the video for a minute and see if you can use this to actually calculate the radius, assuming so see if you can figure out how to calculate the radius from this picture, assuming you knew the measurements of like the height of this building and the length of the shadow, etc. Okay, but I'd like to place one more constraint on us, because this astronomer had a tool that I don't want to assume that our bug here has, and that is they use the sun, right? They use the shadow cast by the sun to do this measurement. Let's say there's no sun in this bug's universe. Maybe this sphere is just in a a well-lit room and there's not really shadows being cast, then if you have that restriction, is there a way to calculate the radius of the sphere? Is there a way for the bug to do this? Well, if you go back and look at our formulas here, you see that the radius comes into play when you're writing out the formula for the area of a sphere. And in fact, even if you don't have a good way to measure area, because that would be, obviously hard for a bug, let's say you could just measure angles, the bug could use these formulas to calculate this radius rho as follows. So one answer to the question is, if I take the holonomy, so I, draw a triangle, calculate the holonomy and the area, and then if I take the holonomy and I divide it by the area, I get 1 over rho squared. And so the reciprocal of the square root of that is going to be our radius. But this turns out to be an important quantity, so let's call this number the curvature. Okay, so that's the official definition of curvature. You draw a triangle, you take the holonomy of that triangle divided by the area, and that gives you some quantity, which we'll refer to as the curvature. Okay, so some things to notice is that on the plane, the holonomy of a triangle is 0, so the curvature is 0 on the Euclidean plane. That's one observation. Furthermore, if I'm on a sphere, then if I increase the radius of the sphere, then the curvature k approaches 0. And so this definition that we have has some nice agreement with our intuition, which is that spheres of larger radius have less and less curvature, and the plane should have no curvature. And by the way, if you're wondering why did we do holonomy divided by area rather than area divided by holonomy, this is an answer to that, because we want, for one thing, we want the curvature to decrease as the radius of the sphere increases, and this has that property. Furthermore, this quantity here wouldn't even be defined on the plane if we had done the reciprocal of it. And so this is a good candidate for curvature. So the next question for you is curvature a local property? And you can think of just the intuitive notion of curvature. Is it a local property or is it a global property? In other words, does it depend on just a small region of the space that you're in, or does it depend on the entire shape of the whole space, right? Like circumference is a global property, but whether a geodesic is straight or not, that's a local property. And another way of phrasing this is, can it change as I move along my space? Because if it can, then of course it must be a local property if it's changing depending on where I am. So the answer is that it's a local property. And the reason is I can easily draw or imagine spaces where the curvature varies depending on where I draw my triangle. So for instance, if I have the Euclidean plane, but it has a mountain on it, then the curvature is going to be different depending on whether I'm here on the flat part or here on the curvy part, right? So if I draw a triangle here in the plane, the holonomy for this triangle is going to be 0, so the curvature will be 0 for that triangle. But if I draw it here, it looks more like a triangle on a sphere. And indeed, this top of the mountain, maybe we can sort of approximate it locally in this region by a sphere. It sort of fits on top of that sphere there. And so the curvature changes depending on where I draw the triangle. Okay, and so if it's a local property, there should be a local notion of curvature. At a point on my surface, at a point P. So let's say P is the top of the mountain here. How can I measure how curved I am at that point? Well, of course, one thing that you want to do if you want to measure the curvature kind of near P is you better, if you're measuring the holonomy of a triangle divided by the area of a triangle, you better choose your triangle to contain the point P, right? Like this triangle I've drawn here is going to be better for measuring information near P than this triangle, which sort of has nothing to do with the point P. Okay, so we choose a triangle which contains P. That's the first step to measure the curvature near the point P. But there's still some sort of stupid choices I can make, right? So in this picture, if I drew a triangle like that, all the variation, all the mountain of this surface happens inside this triangle, but the triangle doesn't really know about that, right? The triangle might as well be living on the plane because on the outside of the triangle, it is just on the plane. And so this triangle is also going to give me a measure of 0 for the curvature. So this is a bad choice. It doesn't tell me much information about how curvy I am near the point P. Okay, and of course, what's the obvious solution? I should choose a really small triangle containing the point P. And in fact, the smaller the better, because that's giving me more local information near P. And in fact, as the triangle gets more and more small, I could do really, really, really tiny one here. That's giving me more and more local information near the point P. I get a more accurate sense of the curvature near P. A more local sense. And what should this remind you of? So we're getting better and better approximations as this triangle gets smaller and smaller. That should make you think of limits. sort of approaching the right number, right? And so what I want to do if I have a point P, start by drawing a triangle, measure the curvature, and then draw a smaller one. That gives me a better sense of the curvature. And then a smaller, and a smaller. And if I zoom in a bunch, I can keep doing this kind of as long as I want to get a level of accuracy as much as I want. And so what's the actual number, which is the curvature near P? Well, it's whatever these approximations are approaching. So it's a limit. And so we define curvature at P, or the curvature near P, to be, again, it's the curvature, it's the holonomy of a triangle divided by the area of a triangle. But I take a limit of these numbers as the triangle gets smaller and smaller, and I'll write it like this, as delta approaches P. In other words, as the triangle gets closer and closer to P. And this is the local curvature. Let's call this K of P. It's the curvature near a point P on our surface. And actually, the Earth is not a perfect sphere. It has some, well, that's not a great picture. But it's actually not quite this bad, but it's an oval. Well, I think it's probably wider at the equator because it spins. So, so this is an exaggeration of what it looks like, but you can see that the curvature around here is going to be larger, smaller radius, than the curvature around here, which looks more like a sphere of larger radius. Okay, so I'm going to pause there so you can collect your thoughts, and then I'll do a second video in a second.